Okay, well, thank you all for joining us for celebration of our associate professors. For the students in the room that have not been, how many have not been to one of these before? Okay, most people have. Congratulations. Good job, folks. So this is something that we really, I'm Dave Barr, I'm Associate Dean for Faculty in the College of Engineering. And this is one of the parts of my job that I like. So we get a chance to celebrate our associate professors and let people know what they've done and where they're going. One of the hardest spots in academia is the rank of associate professor. You've successfully gotten tenure. Congratulations to Aaron and to Vivek. And now the question is, what's next and how do you get to full? And it's an opportunity for us to both congratulate them as well as hear what they're doing and talk about next steps. And I think we're really going to appreciate that. So with that, I'm going to turn it over to Professor Grohl to introduce our first associate professor, Aaron Morris.
Thank you, David. Really appreciate it. As introduced, I'm Eckhard Grohl. I'm the head of the School of Mechanical Engineering, and it's my great pleasure to introduce Aaron Morris as the first speaker of this lunch event. Glad to see so many of you come out and being here. So Aaron is one of our young, dynamic, and wonderful associate professors in the School of Mechanical Engineering. As Dave said, it's a interesting time in a faculty career to step up and really decide what they want to do with their life and their career. His research focuses on the modeling, the dynamics and fluid flows of particulate matters, any type of particulate materials. He has received an NSF Career Award in 22 for developing a novel Monte Carlo method to simulate fluidized particle beds and improving the computational speed by up to 3 orders of magnitude compared to previous methods. He also works a little bit on heat transfer in addition to fluid flow, where he models like the heat transfer in particulate media to optimize thermal batteries and, for example, for application in concentrated solar power systems. His work is, in addition to NSF and other sources, heavily supported by the Department of Energy. And there he has developed novel models for energy storage technologies using these particulate matters. And has also been issued a patent in that field, and in particular a patent on, if I saw this right, allowing the system to operate continuously like a fluidized bed, which can be challenging and avoid costly transient behavior. And that particular patent has also been mentioned by Nobel laureate and former Secretary of Energy, Dr. Stephen Chu. Quite interesting work. I'm looking forward what he has to say about his journey in academia. But please help me in welcoming Professor Aaron Morris.
Yeah, well, thank you everyone for attending. And thanks for, I guess, Andrea's here. This is the first presentation I've given that she's seen. And might be the last, but we'll see. All right, so starting this talk is kind of going back to, where I come from and all that. So I come from upstate New York. The weather's a little bit colder than here, but this is a picture of Albany. And kind of thinking about my journey going back to the beginning, in high school, I wasn't really the best student. I was a pretty bad student, I'd say, especially in French class. And I remember my French teacher pulled me aside and she said, college isn't for everybody. You might think of something else. So it might have been a motivation for me to kind of get my act together. So I guess when I was in high school, a career in academia is probably one of the last things that was on my mind. But at the time, I was pretty good at music. I was pretty good at math and science, and I was thinking about going into making a career in music performance and things like that. And then somebody pulled me aside there and said, well, if you're not unsure about music, it probably isn't the right career for you because it's a really hard path. So then I decided to go the easier path and go into engineering and science. So then I went to Rensselaer Polytechnic Institute. This was just about 20 minutes away from where I grew up. And my first foray into research as an undergraduate researcher, and I was working with Professor Kaminsky. And this was back in 2004, and she had this idea about using neural networks to try to couple neural networks with some heat transfer simulations to develop surrogate models and things like that. And at the time she was saying, well, it's like, I'd like to have a graduate student to work on this, but she couldn't find any interest from sponsors in doing anything with neural networks. So kind of looking back at it, one of the lessons is, well, sometimes you have really good ideas, but it takes a long time in order for those ideas to actually translate and to convince other people and to get other people to support that. But yeah, she was the first introduction to research. And after this, I went to the Jet Propulsion Laboratory for a bit, because even after undergrad, I wasn't quite sure about, do I want to go to graduate school? Do I want to get a PhD? Things like that. So I went out to California, and the weather at the time was a big factor in it. So I drove across the country and started a week later. And I had all these visions about what it was going to be like working at the JPL. One of those was, I get to work on spacecraft and all these fancy rovers and fun things. But then after I got there, they said, okay, your job is to size heat straps for this test that we're doing. So I spent several months just looking through tables and saying what the thermal conductivity is and all these great things. But if I looked across the hall, there was a group, and they were shooting probes through sheets of ice and then deploying underwater rovers to explore. They operated under buoyancy to explore underneath ice sheets. And everybody that was working on this project was doctor. So then I said, well, if I want to work on some of the really fun projects and interesting ones, probably should get a PhD. So then I went to the University of Texas at Austin. If anyone hasn't been there before, I was thinking about showing a picture of UT Austin, but this is kind of, Austin was such a fun city on it, so this is a statue of Steve Ray Vaughan up at Zilker Park looking over the downtown. My advisors were Phil Varghese and David Goldstein, and I'll talk about the research in a second, but David Goldstein, he had a real good sense of humor, and he was, he kind of sensed that academia wasn't quite on my mind, but he was trying to plant seeds of, maybe you want to think about going to academia. So the best sales pitch he could come up with was, if you become a faculty, you can buy a parking permit. Because at the time, graduate students, you couldn't get a parking permit, and you had to, now you can't even get street parking there anymore. So my research at UT was space-related. So I was looking at the problem of rocket plume impingement. So this is an example. I guess since it's Purdue, I should have gone back to Neil Armstrong's video, but this is one of the later ones. That's a landing video, and you can see there's a bunch of dust that's kicked up. So at the time, NASA was interested in kind of going back to the moon, still are. But they wanted to understand the problem of when the rocket hits the ground, it kicks up dust, where does that dust end up going? So did a good amount of analysis on these systems, but then in 2008, there's some economic issues, and NASA changed directions a little bit. Instead of looking at landing on the moon and building a lunar outpost, then they kind of pivoted towards, these private companies, there's incentives to land on the moon, and they wanted to understand if they land near one of the old Apollo sites, are they going to erode the footprints and things like that. So the PhD kind of pivoted midway through. So I guess one of the lessons learned there is, at least in research and academia too, to kind of be nimble, being able to adjust from one situation to another, and I think that's especially true today. So after University of Texas, I went to Colorado Boulder, and the outdoor scene was a big motivator for it, but I was pretty lucky because I found a good mix of work-life balance on it. It was a really good research group and also a lot of fun. So I think my first year there, my postdoctoral advisor, she went on a sabbatical, and so then that freed up all work hours during the day, so it was a lot of go skiing during the day and then come back and do the science and writing and all that stuff in the evening times. And I think I had maybe 40 or something days of skiing in that year, but it was still productive research though, but it's good work-life balance. So what I was working on there, this was my postdoc advisor, Christine Renya. And what I was working on was kind of the first start of working in solar energy. And with my PhD being NASA and aerospace, found it actually kind of, at the time, it was difficult to find a lot of applications and funding for kind of the rarefied gas flows and things like that. But it really introduced me to particle flows that have a whole bunch of interesting physics. And then there's a lot of, I think, impact because the particulate systems are not just some abstract thing of landing on the moon, but a lot of systems on Earth deal with particle flows. So what this project was working on is a concentrating solar power field where radiation heats the tower. You pour a heat transfer fluid in to harness that heat, and then you can release it later. So we were doing kind of some fundamental simulations of just what is the heat transfer to those flowing particles. So what was interesting is you get a bunch of flow instabilities and things like that. So scientifically, it sparked my curiosity, and then there's application to it as well. So then, after the postdoc, went to the National Energy Technology Lab. So now I was getting a little bit closer to academia, but I wasn't quite sure if that was going to be my thing. And I'd say with NETL, this is kind of where it clicked for me that I should probably try to pursue a career in academia. And what I was working on here was a project that was treating basically low-grade nuclear waste on it. And they, just to kind of describe it, they shoot in sodium-bearing waste to a reactor and they process it to clean it up and all that. But they were having issues, so they wanted some modeling work to explain what's going on in the system. And once we got an answer, my supervisor said, well, the sponsor's happy, let's go move on to other things. And I wasn't satisfied with that because I knew all the model assumptions and things like that, that I didn't believe that it should work as well as it did. And I was kind of curious about, well, we should test this more to see if it's how good it actually is. And then it was really, well, you can do it, but do it on your own time and don't show the sponsor because we don't want to raise too many questions about it. So then on my own time, it's like, well, it's a good time to start thinking of different research proposal ideas, and then kind of evolved into research statement and applying to different academic positions. At the time, so this was back in 2015, 2016, our son was born. So this is him lying on the cat flutie, so family increased a little bit. And applying for academic positions or starting an academic career with a young baby, it's challenging. But then you can also look at him and how he's grown over the years, and it's a nice visual indicator of just how time moves quickly in academia. All right, so kind of going through my work here at Purdue, I started off and I was interested in kind of modeling and fundamental research and really wanted to work on the problem of scale up of these particulate systems, trying to use modeling to simulate larger and larger systems. And in general, as you try to resolve a larger system, it takes more simulation time, but you have to make assumptions, and that can reduce the fidelity of it. So my first couple of PhD students, we were kind of talking about this and trying to come up with Monte Carlo approaches to accelerate things. So my first student, Andrew Hong, he did a bunch of two-particle simulations and lots of line plots and quantitative things to make sure we're capturing all the physics correctly and things like that. So it's like two-particle systems and extracting curves. And one thing I realized in academia is you don't have time to do the research yourself often. You rely a lot on your students. And Andrew was a really big help. He generated a lot of preliminary results that then were able to feed into a proposal for the American Chemical Society. So that's the first kind of independent grant I got, or sole PI grant. And then they funded this work to kind of expand upon it, where we now started looking at multi-particle systems, and then this generated preliminary results that then were able to convince NSF. Took a lot of failure to be able to get support from NSF, but eventually did. And then the support from NSF came, and then was able to bring on the next generation of students. So Mohammed has kind of started working on just further accelerating these things using some machine learning tricks and Monte Carlo sampling. And so we started off with two-particle systems, and now these are in the order of 1 million particles in fluidized beds. That's much faster than traditional methods. And now, as a current student, Matt Black is kind of working on extending this even more to larger systems. So this is a pretty grainy one because this is just think last November, October, where this was done. But now he's able to get up to systems 16 million-ish particles on a single computer. It's quite a bit faster considering when I was doing my postdoc on this work, it was about 5 million particles and running on a supercomputer with thousands of cores on it. So it's been a lot of progress there. Other aspect of the research is in more applications. So as was mentioned with concentrating solar power. So this is one of the first PhD students working on this project. It was sponsored by DOE and collaborating with NRO. And basically the question is just, well, we want to use particles because it's inert material for this solar power system, but we can't just look in a textbook to see what the heat transfer coefficient is, and the dynamics here are all very challenging because there's flow instabilities, and it's a complicated process. So Jason, he did some work doing some kind of lab scale experiments and then doing some modeling for it, and then that led to future graduate students. So Krutika, she's graduating this May. She was able to take high fidelity data and then develop kind of heat transfer correlations and then actually validate it through some experiments with collaborators at the School of Mines. And in addition to kind of model validation and kind of linking the fundamental physics to application, we also kind of find some really interesting flow patterns about how particles behave like a fluid, have very similar flow instabilities that you would have in other systems. If you had like a dense fluid sitting on top of a hot fluid, you get same sort of instabilities that form in granular flows as in molecular fluids. So there's always a connection to the fundamentals. And then Chatusha, who's also a PhD student, is looking at connecting what Krutika has done at this kind of particle scale in there and looking at the heat transfer and then extrapolating that to analyze the system performance of these new solar power plants on it. It's really what the goal is to use modeling in conjunction with some experiments to try to reduce the risk of companies adapting this technology. So proving that these things can be a clean energy source that's going to be economically viable. So finally, just going through, I realized a lot of the stuff is, I think there's a lot of good luck that goes on in life where, things happen in your life, you meet people and they give you some advice, and then it turns out actually maybe years later you realize, oh, this is actually really helpful. So kind of acknowledging my mentors, undergraduate research, Professor Kaminsky, my PhD advisors, Phil Varghese and Dave Goldstein. And then at Colorado, Christine, and then at Purdue, Carl Waskern is really helpful for giving feedback and encouragement on some proposal ideas. And also want to acknowledge the students. So all my PhD students, they did the work on it, and you kind of guide them in directions, but they help generate the preliminary results and the papers that help keep the group moving forward. And lastly, Andrea. So there's countless times when working on proposals and not doing as much house cleaning and things like that as I should. And she took a lot of care of Austin too when he was young, and I try to balance things, but really I would not be able to do any of this without her sacrifice and and supporting me. So thank you.
Thank you, Aaron. Wonderful presentation. Any questions from the audience? We have a microphone here. Anybody wants to go first? Have a little bit of time. If not, I can start out, right, and ask you some questions. But you mentioned work-life balance, which I think is very important for anybody's in life, right? And sometimes maybe neglected for faculty that are going through tenure process to some extent. But what advice would you give people, right, that are in the tenure process right now, right, based on your experiences here at Purdue?
That's a good question. Because on the one hand, everybody talks about work-life balance and how it's important, and then On the other hand, it's more papers, more students, more funding, and time is a limited resource on it. So I think the best thing you can do is really commit that as a value that you have and say, okay, I'm going to do this because it's important for my mental health, even if that means I get one fewer paper done or one fewer proposal written.
Jay, go ahead.
Aaron, I was delighted that you decided to come to Purdue from a great career. Question I had was, I think Professor Grohl mentioned one Nobel laureate, Stephen Chu. Did you come across or have interaction at Austin with, and I know you're smiling, so you know I'm going to ask about Goodenow, and just a wonderful mentor for so many and saw so far into the energy grand challenge problem. So could you comment on John Goodenow's influence on you?
Yeah, so when I was at UT, it was in a different department, so I didn't really interact much with them. But in the postdoc afterwards, it was constantly, oh, you were from UT, did you get a chance to meet with this person? And eventually went back to Austin, met with them for a little bit to talk about these sunshot initiatives and things like that. But yeah, it's just amazing all the things that go on around you that you have no idea that were there until you leave, and then come back, and it's you can have good interactions.
Thanks.
Mm-hmm. Any other questions? It's a quiet audience today. I will continue. I still have a couple minutes, right? We also like in these seminars of our associate professor, we like to look back a little bit about your past and what you learned from that, but then also like to look forward. So what's the next great thing for you to address in your career? What's on your what's your plan?
So I guess a couple of things that are of interest to me, and one is with this concentrating solar work. It's finally gotten to the point where they're doing pilot scale testing of this with collaborators in Saudi Arabia on it. So I would love for it to get to the point where this actually becomes a reality and we can demonstrate economic viability. I'd say my real passion though is in the fundamentals, and fundamental science it's a little bit tougher to get funding for, but some things that I want to try doing are using basically using properties of particles as a design parameter that you can have, where you can manipulate particles at the particle scale and then use that to control how they perform in an actual system. And that's something that's not really done too much, but I think it could be an interesting way in the future.
Yes.
Yeah. Thank you, Professor Aaron, for the wonderful talk. I had a question on your NSF grant, which you mentioned. You said that there were a lot of struggles to get it. Can you please tell your learning in it and like how you defined your research objective and so? Thank you.
Yeah, so that's a good question, and I don't fully have that figured out because you still get lots of rejection from NSF. But I think the learning is when you have an idea and you think it's a good idea to get I think the first time I submitted this idea, you get some feedback from reviewers, and some reviewers are encouraging on it and say, yeah, that's a good idea, but no. And then reviewers are more harsh on it and say, oh, this will never work. But I think if you're kind of persistent with it and you keep going, kind of believing in yourself a bit helps. And also speaking to your mentors. So I spoke to Carl quite a bit about the NSF work before it was funded, and he was always encouraging, saying I should keep on going for it. And Andrea was also very helpful with the NSF proposals and things like that, because she can look at these writing from someone's eyes that aren't somebody that knows a bunch about particular materials. So she was able to kind of help consolidate what I was trying to say into a more digestible form.
Yeah, I think that's an excellent point, and a shout out to Andrea. She is working for the School of ME part-time as a technical writer, and we're relying very heavily on her. So thank you for all that you do for the school. Thanks.
Little sales pitch, yeah. She has a 100% track record with NSF career grants.
All right, any other questions?
In your
Hold on. I think we need to use the microphone for.
in your particle-laden flows, are there any bio and biomedical applications, and do you see yourself writing NIH grant proposals in the future?
Yeah, so actually is kind of talking about sabbatical and things like that. That's actually an area that I'm interested in going to. Tried a couple of times for some NIH, FDA related funding. Hasn't quite worked out, but I think it's a really interesting avenue to go.
So when I asked you the question what's next, actually I expected I'm going on sabbatical. That's like after going through this process, right? It's a really nice thing. So I would like to thank Aaron one more time for the presentation and answering our questions. Thank you very much.
Yeah, thank you.